This video will be about how to find limits. The easiest way to find a limit is just by plugging it in. So the limit as x approaches a of f of x, what you can try is f of a. So for example, if I have a function f of x equals x squared minus 4, and I want to find the limit as x approaches 3 of f of x, then all I have to do is try f of a. So f of a, in this case, is f of 3, which is just equal to 9 minus 4, or 5. So I find that the limit equals 5. Sometimes, however, that doesn't work. Imagine if we had a function f of x that was equal to x squared minus 4 over x plus 2. If I wanted to find the limit at a normal point, so let's say limit as x approaches 0 of f of x, then I could just plug it in. And that just equals f of 0, which is negative 4 over 2, or negative 2. But what if I try to plug in negative 2? The limit as x approaches negative 2, f of x, and so I'll try to plug in negative 2, and I end up with 0 over 0. And we get this error where we can't divide by 0, and we really don't know what 0 divided by 0 is, so we can't find the limit. What do we do now? We can use the technique factoring. So we can factor our denominator and numerator. In this case, only our numerator needs factoring. And then we see that we have some like terms here that can cancel. When we do this is essentially we're saying that the two functions on either side are almost the same. But the reason why I put a squiggly line is that in fact they're not the same. One of these, the one on the left, has a hole at x equals negative 2, where the function does not exist. But the function on the right side doesn't have this hole. If I were to graph these, the one on the left, given by x squared minus 4 over x plus 2, would look something like this line, except that at x minus 2, there's a gap where the function doesn't exist. Whereas if I were to graph x minus 2, then I would just have a straight line. But besides this point right here, the functions are exactly the same. So when I'm taking limits, as far as I'm concerned, I might as well just be looking at this equation. So now let's go back to the limit that we were trying to find. X is approaching negative 2, x squared minus 4 over x plus 4. What we can do is replace f of x with the function that we found that was almost exactly the same, x minus 2. And so now we can just use our original plan of plugging it in. So we can just have negative 2 minus 2, and we find that the limit as x approaches negative 2 is negative 4. So now we see how powerful the limit is, because even though our function doesn't even exist at negative 2, we can still find out what it approaches. Another tool we can use to evaluate limits is conjugation. So let's take a case where f of x equals 3 minus the square root of x over x minus 9. Now what happens if we try to take the limit of f of x as x approaches 9? If we just try to plug it in, then we end up with f of 9 equals 3 minus the square root of 9 over 9 minus 9, and we get this error where we divide 0 by 0 again, which we really can't do. So instead, we can try conjugation, where we multiply the top and bottom by the conjugate. So we'll take our numerator, multiply it by 3 plus the square root of x, and do the same with our denominator. So this gives us, on top we have a 9 minus x, and on the bottom we have an x minus 9 times 3 plus the square root of x. Now what we can see is 9 minus x is negative x minus 9. So we can rearrange this as negative x minus 9, and then an x minus 9, 3 plus the square root of x. And so again, what we can do is cancel these out and get a function that is roughly the same. So it's negative 1 over the square root of x plus 3. So now, if we want to find the limit as x approaches 9, then we can just plug it into our approximated function. And that just gives us negative 1 over the square root of 9 plus 3, or negative 1 over 6. What if, for our last function, where we had f of x equals 3 minus the square root of x over x minus 9, we had no idea what to do, and we didn't know what conjugation was, and we had to find the limit as x approaches 9. One way we could do this is, if we use a calculator, we can plug in values that are very, very close to 9 to see what we get. So, for example, if we plug in 9.01, we get that f at that value equals negative 0.166. If we plug in 9.001, then we get the function at that x value to be equal to about negative 0.166. You can bring this continually closer. So if you were to plug in something like 9.00001, then you would get a value really close to what you would get from actually evaluating the limit. Because when we actually evaluated the limit, we got negative 1/6, which is pretty much what these decimals are.